Okay, so position time graphs. They're a really important tool for us in physics. They can tell a lot of information or communicate a lot of information in a pretty concise way. And the setup of these position time graphs always pretty much looks the same. On our y-axis, we have position, which is just where something or someone is relative to some zero. So I'll talk about like defining zero in these problems in a second, or in position time graphs in a second. But on the x-axis, that's where our time is. And so since position is on the y-axis of these position time graphs, then all of these y values then are positions. And we'll look at a specific example in a second of that. That also means that the y-intercept, let's just say that we had a position time graph that looked like this or something. This y-intercept, where our graph crosses the y-axis, of course, we remember from math class, that's where this object or this person starts out once we started timing this, right? At time is equal to 0, or when our x-axis is at 0, when the x value is 0, that's where the position of this object or this person or whatever it is, that's where it's located at first, relative to our 0 down here. And the slope on these graphs, so how steep or how shallow, and the direction of this slope or the sign of the slope, tells us the velocity. And remember, velocity is basically just how an object is moving. So when we look at an example of this, and I'll bring this up right now, then we can get a lot of information. There's a lot going on in this position time graph, but we'll break it down step by step. So at first, we're looking at where this moving man starts. So this is a very old simulation, but it's helpful for us for illustrative purposes. So the fact that this guy starts out at 6 meters, not at 0 here. We've arbitrarily picked 0 in the middle here. But he starts out at 6. So that's why at time is equal to 0, we're not starting out at position is equal to 0. We're starting out at 5.958, basically 6 meters. I'll call it just for simplicity right now. But then notice, and I'll hit play right now, we can see this guy moving to the left, a little bit closer to 0. Let me turn the play speed up here for us a little bit. And then notice what happens when the slope gets steeper. He starts moving a little bit quicker. And maybe an even better illustration of this is this one. So if I have this little stick figure here, notice when I move him slowly, when I move them slowly, the line is kind of shallow. And then if I move really quickly, the line is going to get really steep. Now notice also that when I'm not moving this stick figure person, let's reset this. If I just bring them out to 3 meters, right around 3, their distance or their position is staying right at 3. Time continues to move though. So it's important to remember that when we're at rest, our position isn't changing, but time continues to march on. The fact that I'm sitting in my seat doesn't mean that time has paused, just that my position is not changing at all. So we see these flat parts when our velocity is 0 or when we're at rest, right? Because our slope is 0. We would remember from math class, horizontal lines have a slope of 0. So our velocity is 0 also, coming back to that really key point from these sort of key points. Our slope is the velocity. So if we have no slope like we had in this full section here, then that means that this guy, this stick figure, this person, was not moving during that flat section of the graph when their slope and velocity were 0. Now, one important point that I want to sort of just highlight for a second, it's often very tempting to see these position time graphs as just a profile of something's motion. But if you play around with this, and I'll put the link for this simulation as well as the PhET simulation over here, the older one. I'll put the links for those in the video description. But if you play around with this pretty quickly, you realize that these position time graphs are not just a profile of an object's motion, because we basically take however they're moving, left and right, whatever direction, and we put it vertically, right? So these position time graphs won't necessarily look like how we imagine motion looking like, but if we know how to analyze them, they can tell us all of the exact same information as if we were watching this person or this stick figure move around that entire time. Now, there's an important sign convention that we need to know, and then we'll go back to that sort of older simulation for a second as a quick example. And that sign convention is that the directions right, east, up, north are all usually considered positive if we're not told otherwise. And then the opposite would also be true. Left, west, down, south are all usually considered negative directions unless we're told otherwise. And the origin of that is really just basically the coordinate plane. So we know in math classes in the past, the positive numbers on the y-axis are up, and the positive numbers on the x-axis would be to the right. And then in the same way, on our compass rose, right, we could have north, south, east, west. And so our negative numbers on a y-axis in math class we know would be down, and our negative numbers on the x-axis would be to the left, and then on the compass rose, that's our west and our south. So I just wanted to quickly point that out as like the origins of these kind of general arbitrary sign conventions. That being said, we will definitely work on some problems this year where you guys define your own coordinate system sometimes, especially when we're working on like an inclined plane and we have something, an object like sliding down a ramp. We might say that down and to the right along this ramp is our positive direction so that we don't have to deal with negatives. But in general, these are the sign conventions that we'll work with unless we decide, or unless you decide as the problem solver, that another sign or sign convention or system makes sense for the problem that you're working on. So let's go back for a second to this moving man example. So notice that when, I'll take this back a second, when he's moving at first, he's moving slowly to the left. That's a negative velocity because his slope is negative. So he moves very slowly in that direction. Then all of a sudden, once this gets a little bit steeper, you can see he speeds up a little bit. Now he's moving faster, still in the negative direction. Then his slope gets a little bit more shallow, but still moving in the negative direction. So now he's moving slowly to the left. Now remember what's going to happen when this goes flat also. Now he's at rest. He's not moving. His position is no longer changing when he's at rest, and yet time continues to march on. So we keep moving to the right on our x-axis because that's time and we can't stop time. But his position is no longer changing when his slope is 0, or when this is horizontal. But now he's going to move pretty quickly to the right. And I want to pause this for a second just to point out that even though his position is negative, he's to the left of our 0 and in this negative position territory. His position is negative, but his velocity is positive. The slope of this graph is positive, and he's moving to the right. So that's just something to point out, that the sign of position and velocity can be the same. They can be different, though, like in this case where we have the negative position and positive velocity. Okay, here we go. So now he passes 0, and then he comes to rest. We can see position not changing. Then he moves very quickly to the right, then a little bit more slowly to the right. And now you probably know what's going to happen next. Now he's moving very rapidly to the left. And in fact, I want to just take this back another second. So in all of these parts from about 13 seconds out to about 15 seconds, this guy is moving with a positive velocity. He's moving to the right, and his position is to the right. However, in this next part, his position is still positive right here in this moment that I've paused it. He's to the right of 0, and yet his velocity is negative because he's moving to the left. His motion is towards the negative direction. And it's really fast because this position time graph is really steep, or it's steep because he's moving really fast. Now he moves to a positive slowly, and now he's at rest to wrap up that motion. And so all of this information, if we just had this position time graph and we didn't have this guy running around in front of us, we could still figure all of this out just from the position time graph. And we're going to work in future videos about telling stories with these position time graphs and actually increasing the complexity of the stories that we can tell as we learn more about this.